Welcome to my Lab 3, Black Hole Orbit. The objective of this lab was to use observational data to calculate the mass of a black hole. The given data in this lab was a CSV file filled with positions of a star as it orbited this black hole, the star's mass, the time step, which was 86,400 seconds or 1 Earth day, and the position of the black hole. The result of this lab was the mass of the black hole, which was approximated to be 3.0989 times 10 to the 31st kilograms. The key assumption in this lab is that the only force acting on the star is the gravitational force of the black hole. With this assumption in mind, we move on to Newton's second law, which states that by observing the motion of a system, the net force acting on the system can be calculated. In order to approximate the mass of the black hole, several steps must be taken. First, we must find the distance between points of observational data of the star. This can easily be done by subtracting an initial position of the star from a final position of the star. Once this distance is calculated, we can use it to find the velocity using the equation velocity equals distance divided by time. Once we have the velocity, we can use it to find the change in momentum of the star using the equation momentum equals mass times velocity. And once we have this change in momentum, we can then find the net force using Newton's second law equation, which says that F net equals change in momentum over change in time. Once all this is done, we are ready to use Newton's law of universal gravitation to find the mass of the black hole. Newton's law of universal gravitation states that F net is equal to the gravitational constant g times mass 1 times mass 2 divided by r squared, where r is the distance between the two objects. We manipulate this equation to create a brand new equation, which states that the mass of the black hole is equal to the net force, or the magnitude of the net force acting on the system, times r squared, which is the magnitude of the final position of the star minus the position of the black hole, divided by the gravitational constant g times the mass of the star. Now that we have our equations and our calculations down, all that is left to do is plug in these values to our computer program that will approximate the mass of the black hole for us. As you can see here, the net force has been entered into the program as delta P over delta T, or the change in momentum over the change in time. F net parallel has been entered as the magnitude of the change in momentum divided by the change in time times the initial momentum divided by the magnitude of the initial momentum. Because we know that F net equals F net parallel plus F net perpendicular can simply be entered as F net minus F net parallel. When we run our code, this is what we see. This black arrow represents F net parallel, and it is pointing in the opposite direction of the star's momentum. This tells us that the star's momentum is decreasing as it is moving away from the black hole. This blue arrow represents F net perpendicular, and it is pointing inwards. This yellow arrow represents the total F net, and it is pointing directly at the black hole. We also see that the code tells us that the average mass of the black hole was 3.0988 times 10 to the 31st kilograms, while it only has a standard deviation of 4.03 times 10 to the 29th. This number is 2 magnitudes smaller than our approximated mass and tells us that our model made an accurate prediction. A key observation to take from this lab is how F net and its components are different from the change in momentum over the change in time in its components. While these two are equivalent, they are still distinct. F net is the unobservable cause, and the change in momentum over change in time is the observable effect. By observing delta P over delta T, you can then determine F net. Now, if we were to imagine that a new black hole was placed where a previous black hole was, yet the motion of the star remained the same, would we be able to tell the difference? The answer to this question is no, as if the gravitational force is assumed to be the only force affecting the motion of the star, and the motion is the same, that means the gravitational force must be the same, meaning the mass of the two black holes must be the same.